In a right triangle, the three sides are defined as opposite, adjacent, and hypotenuse. When you construct a right triangle, a square is placed in the 90-degree vertex. The theta represents just some marked angle within the triangle. Your 6 trig functions are defined by that angle's location and 2 of the 3 sides of your triangle combined. Now, the very top right equation, if you're given 2 of the 3 sides of a right triangle, you can use Pythagorean theorem to find the third side. For example, if you're given opposite and adjacent lengths, you can square each one, add them together, and that will be the length of the hypotenuse squared. The hypotenuse is always the longest of the 3 sides in a right triangle. The most common trig functions that are used are sine, cosine, and tangent. Sine is of whatever angle is marked off is defined as the length opposite of that angle divided by the length of the hypotenuse. Cosine is adjacent over hypotenuse, and tangent of that angle is defined as opposite length over adjacent length. The other 3 trig functions, cosecant, secant, and cotangent, are just the reciprocals of those 3 on the left side that you see. So on the next slide, we're going to look at a right triangle where 2 of the 3 sides or lengths are given, and we're going to use Pythagorean theorem to get the third side, and we're also going to find all 6 trig values. In this right triangle, we are given the 90-degree square. Theta is marked in the lower right vertex, and we're asked to find the exact values of the 6 trigonometric functions of theta that's shown in this figure. Okay, first thing is we need to find that bottom leg, and it's going to be representing the adjacent side to theta. The short side, I'm just going to mark it temporarily with an X. The 2 shorter sides, when you apply Pythagorean theorem, those are the ones that stay together. So the 2 legs that form the 90-degree, keep them on the same side when you build your equation. The hypotenuse will always stand alone in Pythagorean theorem. And so that's going to give us 144 plus x squared equals 169. Subtract 144. And then finally take the square root. What's the square root of 25? 5. So I'm going to take off this x and put the length of 5 there. I'm actually going to leave the x, but I'm going to scoot it over. And that way later you can tell where the x had to go in that equation. Now that we have the triangle completely diagrammed, let's go and write our 6 trig functions. Okay, so from the location of theta in the triangle, sine is opposite over hypotenuse. So that gives us a ratio of 12/13. Cosine from theta is adjacent over hypotenuse. And finally, tangent. And it's a good idea. If you get comfortable with these 3, then the other 3 are just reciprocals, flipped over fractions. Tangent is opposite of theta divided by adjacent to theta. Our reciprocals are just going to be 13/12 13/5, and 5/12. There's a wonderful little acronym that will help you keep this side straight, and it's Sohcahtoa. Some old horse caught another horse taking oats away. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Let's do one more example. I'm going to take a right triangle, and here, let me get my black marker on here. And I'm going to do this one where we're not given the hypotenuse. We're just given the two legs. And I'm going to mark theta right there. Okay. The 4s are on the two sides that form the 90-degree angle. So when we set up Pythagorean theorem, we'll actually have to find the hypotenuse. On the previous example, we were given a leg and a hypotenuse. But the equation works no matter what. As long as you've got two of the three sides, you can always find the third. That's going to give us 16 plus 16. Okay, that's still going to be our hypotenuse squared. 32. Square root of 32 will be the length of our hypotenuse. 32 can be written as 16 times 2, which will reduce to 4 square root of 2. And that's the length of our hypotenuse. Now we're ready to define our 6 trig functions. Sine from where your angle is marked is opposite over hypotenuse. Opposite over hypotenuse. Your 4s cancel. And if you have a radical term, many times you're expected to rationalize it. And for this one, we're just going to take our square root of 2 and multiply the top and bottom of that fraction by that value. The part in red is really just a clever 1, so it's okay to do it. That gives us square root of 2 over square root of 4. Cosine will be the same thing, adjacent length over hypotenuse. And I'm just going to go ahead, it'll be the same simplification as we did for sine. Square root of 2 over 2. And tangent, opposite from theta over adjacent to theta, and that's a 1. Now I'm going to go in here and mark in blue this 1 over square root of 2. That's the value of sine before we rationalized it. For me, that's totally fine. And if WebAssign will take 1 over square root of 2, type that in. It's not a wrong value, it's just not rationalized. Now, the reason I'm highlighting that is when we get ready to do the other 3, cosecant, for example, its sign flipped over. 4 square root of 2 over 4, the 4's will still cancel, but it'll be a clean square root of 2 over 1, but you don't have to write the over 1. Secant, same thing. Hypotenuse over adjacent, reduce the 4's, you get a clean square root of 2. And then tangent was 1, flip it over, that's still 1. And so these are the other 3 trig values. But I just wanted to highlight that in blue because if you ever have a fraction that's not rationalized, the reciprocal identity will just be that one in the blue box flipped over. In this chart, you are given the common 3 trig functions, sine, cosine, and tangent, and their special values for the acute angles. They're the special marked off angles. We're going to refer to these quite a bit when we get into the unit circle part of the class. For now, I just wanted to make you aware of them, and I put a little note at the bottom of the page for a really nice chart that looks professional, and it'll probably contain the other 3 values. If you'll go to Google Image and just type in special trig values of acute angles, you'll get a whole bunch of different options for a real pretty chart. Your e-text will certainly have them if you go to Chapter 6, Section 2, the one that's titled Right Triangle Trigonometry. But like I said, if just a quick Google image, if I find a real nice one, I'll probably put it on your Google Drive under the Formula Sheets folder, and that way you can access those as you need to. But if you wanted to Google image this, print you off a nice copy and just have it close to do your homework and your quizzes and tests, whatever, that's totally appropriate. Okay, and this next example, we're going to sketch a right triangle from information given. Let's take sine theta equals 3/5 and find the other 5 trig functions values. Okay, so let's remember sine, that's the SOA part. The SO, S-O-H, and that's from the Sohcahtoa acronym or little catchphrase, however you want to put it. That does tell us that if we construct a right triangle, I never draw them to scale, I just draw the best triangle I can every time. Mark off an angle, just let it be theta. Sine is opposite over hypotenuse, so from theta, opposite hypotenuse. Well, the bottom side, which is adjacent to theta, we don't know that yet. That side squared plus 3 squared, those are the 2 sides that form the 90-degree angle, will be equal to the hypotenuse squared. 9, 25, subtracting 9, and square root. And so our adjacent length is 4. Sine is already given, so now it's just a matter of writing the other ones. Cosine, adjacent over hypotenuse, tangent, opposite over adjacent. From these alone, we can get secant and cotangent. Secant will be 5/4, and cotangent will be 4/3. We were given sine. What's its reciprocal? Exactly, cosecant. And so cosecant will be the reciprocal of 3/5, which is, that's right, 5/3. So now we've got them all. And for our final example in this video, we're given that the tangent of theta is equal to 5/6. Tangent is the toa part of Sohcahtoa, that's opposite over adjacent. And again, that's opposite of where theta is marked. If you were to mark theta in the top vertex, your 5 and 6 would just be changed places. Okay, 5 and 6 form the right angle, so 5 squared plus 6 squared is equal to that hypotenuse squared. 25 plus 36, what's that equal to? 61. And so x is going to be square root of 61. That's our hypotenuse. Okay. Now since tangent is already given, I'm just going to sneak in cotangent right here. It's the reciprocal. Now the other four, let's see, sine is opposite over hypotenuse. That's 5 over square root of 61. If you're required to rationalize, then that's going to be multiplied by square root of 61 top and bottom, giving us 5 square root 61 over 61. Before we rationalized the 5 over square root of 61, if you wanted to go ahead and flip that, that's going to give you your cosecant value. Those are reciprocals. Now let's get cosine. Cosine is adjacent over hypotenuse. Adjacent over hypotenuse. Rationalized. And that's going to be 6 square root of 61 over 61. Now that fraction and the one above it, 5 and 61 won't reduce anymore. And I'm talking about this 5 and that 61, this 6 and that 61. If they are reducible, you can absolutely reduce those. Now don't reduce under the radical, but anything out from under, you can reduce. Like if that had been say a 5 over 65, you could reduce. Or a 6 over 60, that's totally fine. But 6 and 61 won't reduce, 5 and 61 don't reduce, and that's fine, they don't have to. And then our final trig function, the reciprocal of cosine is secant, and you can use that fraction before the rationalization to get that value.